All right, let's dive right in. Today, we're tackling the absolutely fascinating and, let's be real, seriously mind-bending universe of Dr. Habdank. This is a world where concrete, established physics smashes right into pure, unadulterated imagination.
And that really gets to the heart of what we're exploring today. What actually happens when you take the super rigid mathematical world of quantum mechanics and blend it with a truly bold, speculative, and artistic vision? That's exactly what we're going to pull apart piece by piece. You know, the analysis of this work kind of gives us our roadmap right here. It calls it a conceptual compendium. So, what does that even mean? Well, it means our goal isn't to prove it's right or wrong. Instead, we're trying to figure out how it's built and to walk that razor's edge between proven science and pure artistic expression.
Okay, so before we can get to the really wild stuff, we've got to build our foundation. We have to start with the bedrock, the real, undisputed science that everything else is built on. First up, the Hamiltonian operator. Now, in the world of quantum mechanics, this thing is a huge deal. It's basically a mathematical machine that calculates the total energy of a system. Its energy from moving around and all its stored up potential energy. Think of it as the engine inside the famous Schrödinger equation, the thing that predicts how a quantum system is going to change over time. Next, we've got this idea of quantum chaos. See, when quantum systems get super, super complex, their behavior can look totally random. So physicists don't try to track every single particle. That'd be impossible. Instead, they look at the statistics of the system's energy levels. It's kind of like trying to understand a massive crowd, not by interviewing every person, but by looking for overall patterns in how they move. And it turns out these patterns really fall into two big categories. You've got your orderly, predictable systems. They follow a statistical pattern called the Poisson distribution. But the chaotic ones, well, they play by a different set of rules, a pattern called the Wigner-Dyson distribution. Now, you're going to want to file that name, Wigner-Dyson, away for later, because it's going to come back in a really interesting way.
So, there we have it. Our bedrock of real physics is in place. Now, for the fun part. Let's see how these solid foundations are used to build something way, way more ambitious, an attempt to construct a totally new vision of the universe.
And it starts with this grand, and let's face it, pretty long title, the function gradient quantum gravity's potential state theorem. Whew, that's a mouthful. But its goal is huge, to try and solve one of the biggest puzzles in all of physics, how to connect quantum mechanics with Einstein's theory of gravity. But the crucial thing to see here isn't the name, it's the status. This is a speculative theory. It doesn't have mainstream scientific proof. So if you thought that was a leap, well, buckle up. What's coming next is like a jump into another dimension. We have the standard Hamiltonian we talked about, and then we have this, the biquantum Hamiltonian distribution. Now this equation, it's presented like it's a cousin to the standard Schrödinger equation, but whoa, it is doing something completely different. It's mixing the familiar idea of energy with this much more abstract concept of order. You are not going to find this formula in your college physics textbook, that's for sure. It's a creative, symbolic model, and it's designed to introduce a brand new idea. Let's just unpack that for a second. The formula has two main parts, a real part, which describes the distribution of energy, and then an imaginary part, which describes the distribution of something called an order parameter. And the big goal? To describe the, get this, energy randomness of a quantum information field at the multi-bifurcation point of space-time. I mean, listen to those words. They're incredibly evocative and cool, but they aren't standard scientific terms. Okay, this brings us right to the core of what we're looking at today. We've seen the real science, we've seen the speculative theories. So the big question is, how in the world do you get from one to the other? How are these mind-blowing ideas actually put together? Well, it turns out there's a method to the madness, and it's a really consistent and frankly brilliant two-step process. Step one is simple. Cite genuine, peer-reviewed science. You ground your idea in something totally solid and real. Then comes step two. You extrapolate or reframe those findings. You take a giant leap, extending them into a new space, often one that's more metaphorical or philosophical, a place the original scientists never, ever intended to go. Okay, let's put this method to the test. Let's see exactly how it works with our first example, the idea of tachyonic fields. We're talking about hypothetical particles that can travel faster than the speed of light. First up, step one,
ground it in reality. The framework cites actual, legitimate scientific papers. We're talking one from a serious physics journal about breaking the light speed barrier, and another from the journal Nature itself about faster-than-light phenomena in certain materials. This isn't junk science. This is the real deal, cutting-edge stuff.
And then, here it comes. Step 2, the creative leap. The framework makes the claim that luxons, which are just normal massless particles, like photons of light, are actually multibifurcation points. Now that's just a really complex, fancy way of saying they are critical branching points or boundaries for these imaginary tachyonic fields. And right there, you see the method perfectly. Take real research, borrow its language, and use it to build a brand new, speculative idea. All right, you ready for another one? Because this next example is even more striking. It's a concept that's called intellect amplification. And it's the same playbook all over again. Step 1, cite real research from top-tier journals like Nature Communications. This research is all about using machine learning and real-time data to stop quantum bits, qubits, from messing up. It's about keeping them stable. This is incredibly important, practical work for building quantum computers. And then, here comes step 2, the big philosophical reframe. This super technical, nitty-gritty engineering process of stabilizing computer components is reinterpreted as something huge. It's presented as a cognitive process, a metaphor for intellect amplification. A practical engineering solution gets elevated into a sweeping metaphysical concept. It's the method in its absolute clearest form. So, okay, we've deconstructed the foundations, we've looked at the grand ambitions, and we've uncovered the method itself. What are we supposed to make of all this? Is this some kind of new physics? I think the key is to see it all laid out like this, all at once. We started on the solid ground of standard physics, like the Hamiltonian. From there, the framework launches into purely speculative theories, like that gravity theorem. Then it introduces these totally non-standard, creative models, like the biquantum Hamiltonian. And finally, it grabs genuine, real research and gives it this huge philosophical facelift. Each piece has a totally different relationship to scientific fact, and altogether it creates this complex, beautiful tapestry woven from both science and art. And that leaves us with one last really fascinating question to chew on. What is this? Is it science? Is it art? Or is it maybe a creative blueprint for what could come next? You know, the line between a bold new theory and a beautiful piece of fiction isn't always as clear as we might think. And it's right there, exploring that boundary, where some of the most interesting ideas are born. Thanks for joining us on The Explainer.